I'm Director of Marketing and Support of Terra Analysis, and today we, with my colleague Alexander Lebimtsov, will discuss features of new version QuickField 5.10 and its practical applications. Let me start from overview of new features. Main changes in QuickField 5.10 comparing to previous releases is actually there are two features we want to highlight today. It's improved measure and two modes of magnetic state import from DC to AC or DC magnetic problems. Measure is one of the main parts of any finite element applications because accuracy and speed of solution or simulations based on finite element methods are very highly dependent on the mesh quality. And QuickField always featured very efficient measures. But in some cases, for complicated topologies and complicated geometries, it was required to make many manual adjustments. As you know, QuickField offers automatic mesh build generation and possibility to adjust any part of mesh or full region. Previously, for complicated geometries, sometimes in some spaces mesh was not optimal. As you see on the slide, some parts of automatic meshes built by previous model editors had sometimes bad points with very narrow angles, with many neighbors for nodes, which was not good, and it caused longer solution time or losses of accuracy, or in very hard cases, the problem may not converge at all. Of course, experienced user usually learn very fast how to adjust mesh manually. But for version 5.10, it is less required because new measure builds optimal meshes for much more complicated geometries when we were able to do it before. There is not much to discuss because it is just better mesh. But believe me, it's plenty of work, and we are very happy that now QuickField becomes more stable and faster for complicated geometries. Other feature we want to show you today is two modes of magnetic state import. Let me tell you a little bit more about import. QuickField is a multi-physical package, and we feature many types of problem formulations, including magnetic, electric, and thermostructural. Some of them allow importing of field results from other applications. And for example, you may import losses from electrical simulation to thermal simulation, or you may import loads from thermal simulation to stress simulation. But it is also possible to combine several simulations of the same type. For example, it is possible to link magnetic DC simulation to AC or DC simulation. What does it mean? If the problem includes several sources, it's sometimes convenient to calculate first the general overall level of saturation of the media and then perform analysis for this specific distribution of working points. It's especially important if you need to simulate problem which is almost linear, but due to different saturations of different parts of magnetic system, you should understand the working point for each part of the media before running simulation. Previously, you need to run transient nonlinear magnetic simulation for such kind of problems, which is very accurate but rather long because you need to make many time steps, and on each of time steps you need to converge to quasi-static solution. Now it is possible to import magnetic permeability from DC problem to AC or DC problem, And unlike previous version featured, previously we allowed import only of static or apparent permeability. As you see, for each point of the BH curve, it is possible to define two types of permeabilities. And in electrotechnology and electrical engineering, two types of permeabilities are used. Apparent permeability, which is ratio of flux density and magnetic field strength, and incremental permeability, which is derivative or slope of the curve. And for many practical cases, it is important to import incremental permeability. So now QuickField features special switch. Then you perform the linking of the DC magnetic problem to DC or AC magnetic problem to transfer the distribution of the permeabilities or magnetic state import. You may select what kind of permeability you prefer to use. It may be either incremental permeability or apparent permeability. My colleague will show you in details how practically make this selection and what results will it give you. But generally, this option allows you to replace transient magnetic simulation by combination of DC and AC magnetic simulation. In many practical cases, it may save you lots of time. System requirements of new version are the same as it was before. We support Windows XP, Vista or Windows 7, and computers which work in single user mode should be equipped with USB port for copy protection key for professional version. QuickField is very modest in memory requirements. We need 2 gigabytes of RAM for individual simulations, but in case you have multi-core system and want to perform serial simulations or optimization with label mover, it may be beneficial to have more memory because you may run several simulations controlled by label mover in parallel, and each process may require up to 2 gigabytes of RAM. So for parametric studies on multiple systems, more memory is better. But with 2 gigabytes of RAM, you may solve practically any problem. And as it always has been, and I hope it will always be, QuickField is very different from other packages because it requires no training. You may start using it with no knowledge of finite element theory. You need to know your physics, and QuickField will provide you tools to do the rest. For customers of older versions of QuickField, update policy is the same as it was before. You may update as a one-time update for 30% of the cost of compatible configuration on current price list, or you may subscribe for 12-month maintenance, which will bring you free updates for this period, and it may well be extended. And all new orders or update orders go with 3-month maintenance included. It was the same as always has been with QuickField. Now, after the short poll, my colleague Alex Lubimtsev, our support engineer, will show you several live presentations with examples of new features applied to practical engineering problems. Let me start the first poll. Please answer question on your screen. What types of analysis do you use most? You may select several answers to this question. Okay. I believe everybody who wanted to let us know the opinion. Did it already? Let's see the results. So our today's audience mostly use magnetic and electric analysis, but there are also people who use thermal stress. So we have very diverse audience today. Okay, now let's continue with presentation. As you know, we always run live simulations in our webinars, and Alex will show you how to apply new features of QuickField 5.10 for practical solve problems of electrical engineering. Thank you.
Hello everybody, my name is Alex, I work in QuickField support team, and today we speak about new features of QuickField 5.10. New features of QuickField 5.10 are dynamic magnetic permeability import and improvements in mesh technology. And today we'll show you some practical cases where you can benefit from these new features. Let's start with magnetic permeability import. Here is the example that we will analyze. This is a filter reactor. The purpose of this device is to smooth the current fluctuations. From my thyristor power source, I get DC voltage and some fluctuations. I place the reactor at the output and hope that its inductance will lessen the fluctuations level. This is my reactor. The usual approach to simulate such devices is to run a full transient electromagnetic analysis. Let's start QuickField. This is my transient magnetic problem. And this is the model. In my model, I have a core, winding negative and winding positive, insulation, and the air outside. So this is the quarter of my full device model. The core is ferromagnetic with BH curve specified. In the winding I have DC and AC current source. And I have to specify the time integration step, as this is a transient problem. I will calculate several steps, and on each step I will calculate the field distribution. Now let's take a look at the simulation result. Here you can see the field lines. I can adjust the field picture. I will switch off field lines and switch on the flux density color map. You can see that flux density distribution is not uniform. And let's take a look at the permeability distribution. You can see that some parts of my core are saturated and some parts are not saturated. And this result I can see for every moment of time. And I can calculate integral values. Here I build the contour. And I will calculate the magnetic flux in my core. And as this is a transient problem, I can see how the flux changes in time. Now this is the time plot of magnetic flux. You can see it is some constant value plus some alternating part. This is fine result, but the only drawback of such approach of simulation is a simulation time. It took me 20 minutes to run full simulation. The result file is about 25 megabytes. Not a very big time, you may say, but it's not a big model. I have only a quarter of my full device. QuickField 5.10 feature the magnetic state import, and with this new feature we can simulate this problem much faster. Please take a look at this curve. The DC current shifts the working point here, and small AC component of the current moves the working point along the curve. As the AC component is small, we can consider the change to be linear. Here you can see this point. And these are fluctuations caused by the AC component. Now, what is new in QuickField 5.10? We can run DC magnetic simulation and find the magnetic saturation level of the core. Then we can import the saturation into the linear AC magnetic problem, and the value imported is incremental magnetic permeability. Let me show you how it works in QuickField. This is my DC magnetic problem. I have the same geometry model. I specify the BH curve for the core. And I specify DC current in the winding. Let's solve this problem. You see, it's only 15 seconds. And now I can see the field distribution again. And I will import this magnetic state of the core into AC magnetic problem. Now this is my linear AC problem. The problem has the same geometry model. As the magnetic state is imported from DC, I do not specify the curve here. The magnetic permeability here is 1, and the actual level of saturation is imported. In the winding, I specify only the AC component of the current. And in the problem properties, I specify the magnetic state import link. I will import the incremental permeability. It is possible to import apparent or incremental permeability. I need to import incremental permeability in my AC problem. Let's run the simulation. Again, you can see the field distribution, and this is the AC part of the flux. So we have two parts, DC part and AC part. Let's compare the results that we get with transient analysis and the results that we get in DC and AC. Now this is the magnetic flux in my transient problem. I can see the same in the timetable. I will copy all the data in the Excel. Now this is the time, this is the flux transient. And what is the flux in DC magnetic? Let's copy it. This is the flux DC. The flux DC is constant, it doesn't change in time. Now this is my DC flux. And here I will copy AC flux. This is my AC problem. This is the magnetic flux, its amplitude and phase. So for AC I should type in the formula. P frequency 300 Hz and time. Now this is the DC flux and this is the AC flux. Let's find the sum of both components. This is the DC plus AC. Now let's compare what we have with DC plus AC with the transient. I will build the plot. I will need flux transient and DC plus IC. Here we are. With blue line, the flux transient is marked, and with green line, the flux calculated with DC plus AC approach is marked. I must say that these are very close values. You can see this by yourself. But of course, transient nonlinear magnetic analysis is the very powerful option, but it's very time consuming too. And comparing to the transient magnetics, the combination of fast DC and AC simulation may be considered as a first approximation. You can see there is some error here, some difference between transient, full transient and DC plus AC. The error of this approach depends on the curvature of the beige plot near the working point. In many practical cases, the result of the first approximation may be quite sufficient, even if the nonlinearity of the beige curve in the working range cannot be neglected. Combined AC and DC simulation may allow to adjust simulation parameters, make rough design changes, and then, as a final step, you can run long but accurate transient magnetic analysis. So this is the new feature of QuickField 5.10. Next, we will continue with the new measure, and now we have a poll question.
Thank you, Alex. It was very interesting. Let me start the second poll we prepared. Please answer the question on your screen. Do you see benefits of using magnetic state import instead of transient magnetic analysis for your task? You should select just one answer. Yes, it is useful, no, it is useless, or you are not sure yet. Okay, it looks like everybody voted already. Let's see the results. And it's very pleasant to know what everybody in our audience today like new features. Good, thank you. Now Alex will continue with explanation about improved measure in QuickField 5.10. Alex, please.
Yes, the next feature I would like to speak about is the finite element measure. Usually you build the mesh simply by clicking the mesh button, and QuickField generates automatic mesh. I will tell you more about how it works in QuickField. Computational algorithm provides most accurate result on mesh consisting of ideal equilateral triangles, like here. Each node should have exactly 6 neighbors, and the system of linear equations which we need to solve has 6 non-zero members in each line. And QuickField tries to build uniform mesh, but in practical cases with many internal boundaries between materials, uniform meshes are either not possible or require too many finite elements. And usually the finite elements meshes are non-uniformal. In such cases, the solution needs some iterations to converge. QuickField mesh generator is based on geometrical principles only. The mesh density will be automatically adjusted to the specific sizes of geometry objects. This means that in large objects we have large triangle size, and in small objects we have small triangle size. But sometimes the physics requires finer mesh in geometrically large objects. Here is the example we will study today. It's an induction heating system. The induction coil carries alternating current at high frequency, and the alternating magnetic field induces eddy currents in the steel tube, and the tube is heated by eddy currents. In the induction heating process, eddy currents are distributed close to the surface of the conducting materials. Therefore, the mesh should be extremely dense on the surface. Let's run QuickField and try to solve this problem. Now this is my model. I have the copper winding here with some AC current, and my steel tube. The tube permeability and conductivity are nonlinear functions. Let's try to build the automatic mesh. I simply press the button and the mesh is ready. Let's simulate this case. It's very fast. We can see the field lines, but let's take a look at the current distribution. Well, from this field picture, I can say that I need denser mesh in the tube. The field lines should be smooth. It's not an accurate result. Let's build the denser mesh. Well, I cannot build the dense mesh in all the area. So for my area, I set the triangle size of 10 millimeters. These circles mark the triangle size. For my coil, I will set 1, and for my tube, I will set 0.2 millimeters. Now let's again build the mesh. Very fine. I have dense mesh in my tube. But let's take a closer look at the mesh near the tube. Please note these narrow triangles here and here. I believe there could be some difficulties with convergence. I remember that triangles should be, like here on the picture, equilateral. But my triangles here are very narrow. Well, anyway, let's try to solve this problem. Please note the fluctuations of the progress indicator. The solving process is not stable, you can see it. For sure, there are some difficulties with convergence. I will check the time required to solve this problem. It lasted after 35 seconds. We can see the field distribution. Good meshes are aesthetically nice looking, and experienced operator can easily find bad regions and manually adjust the mesh. Let me show you how you could do this. I will simply add the node here and change the mesh size here. Now let's build the mesh. You can see it's much better now. There are no more narrow triangles in my model. Let's run the simulation. You see the solution process is fast going without fluctuations, and only 6 seconds, 6, and I can see the field distribution. This is how it works in QuickField 5.9. You build the mesh, carefully observe it upon narrow triangles, and try to fix the problem. Now let's see how it works in QuickField 5.10. Here is my original model with bad mesh and with narrow triangles that was generated by version 5.9. Let's rebuild the mesh with new version. How does it look like now? I think much better. No more narrow triangles. Element shapes are almost equilateral triangles now. Let's run the simulation. One second, 2 seconds, 3, 4, 5, 6, 7. And we can see the field distribution. It was 30 seconds with previous version until we adjusted the model. The improved measure in QuickField 5.10 builds fine mesh in most difficult situations. It allows user to concentrate on physics and save time on mesh refinement. These are all new features I wanted to show you. I hope you will find them useful. Thank you.
Thank you, Alex. It was interesting. Do you have any questions? Okay, so it looks like all was clear. And if you have any questions, please feel free to ask us by email or using our online chat system through our website. We will publish a recording of this webinar in a few days on our webinar archive and on YouTube. And we are having extensive plans for future webinars, so please stay tuned with us. We will announce our webinar program soon. And for today, we have no more to tell you. Thank you very much for coming today, and hope to see you at our future webinars.